Welcome to an intriguing journey into the heart of the universe, where we explore the captivating contrast between matter and antimatter. At the most fundamental level, the universe is composed of particles that make up everything we see, touch, and experience. These particles, known as matter, are the building blocks of the cosmos. But there's a mysterious counterpart to matter that challenges our understanding of the universe: antimatter. In this exploration, we'll delve into the definitions, properties, and the profound differences between these two entities. We'll also touch upon the latest theories, research, and the potential implications of antimatter in science and technology. So, buckle up as we embark on this fascinating quest to unravel the mysteries of antimatter versus matter. Matter is the substance that makes up all physical objects in the universe. It is composed of atoms, which are the smallest units of matter that retain the properties of an element. Each atom consists of a nucleus, containing protons and neutrons, surrounded by electrons. Protons are positively charged, neutrons are neutral, and electrons are negatively charged. Matter has several key properties, including mass, volume, and the ability to interact with gravity and other forces. Mass is a measure of the amount of matter in an object, while volume is the space it occupies. Matter is affected by gravity, which is the force that pulls objects toward each other, and it can also interact with electromagnetic, strong, and weak nuclear forces. Matter is not just the stuff around us. It's the very essence of the physical universe. It's composed of atoms, which are the basic building blocks of everything from the air we breathe to the stars in the night sky. Atoms themselves are made up of even smaller particles: protons, neutrons, and electrons. Protons and neutrons form the nucleus of an atom, while electrons orbit around this nucleus. The way these particles are arranged and interact determines the properties of matter, such as its state, solid, liquid, gas, density, and how it reacts with other forms of matter. Antimatter is the mirror image of matter, consisting of antiparticles that have the same mass as particles of ordinary matter but opposite charges and other properties. For every particle of matter, there exists a corresponding antiparticle. The existence of antimatter was first predicted by physicist Paul Dirac in 1928, and the positron, which is the antiparticle of the electron, was experimentally discovered by Carl Anderson in 1932. This discovery opened a new chapter in our understanding of the universe. Antimatter is not just a concept from science fiction. It's a real and vital part of the universe. It's essentially matter with a twist. Every particle has a corresponding antiparticle with the opposite charge and other quantum properties. For example, the antiparticle of the electron, known as the positron, has the same mass but a positive charge instead of a negative one. This discovery was a groundbreaking moment in physics, opening up new avenues of research and understanding of the universe. The relationship between particles and antiparticles is a fascinating aspect of particle physics. Each fundamental particle has an antiparticle counterpart. For instance, the electron's antiparticle is the positron, the proton's is the antiproton, and the neutron's is the antineutron. These antiparticles are not just theoretical constructs. They have been observed and studied in laboratory conditions. The creation of antiparticles often occurs in high-energy processes, such as those found in particle accelerators or cosmic ray interactions. The most obvious difference between matter and antimatter is the charge. For example, electrons are negatively charged, while positrons are positively charged. Similarly, protons and antiprotons have opposite charges. Matter and antimatter interact with fundamental forces in the same way. For instance, both are affected by gravity and electromagnetic forces. However, the annihilation process is a unique interaction where matter and antimatter particles convert into energy. When a particle of matter meets its corresponding antiparticle, they annihilate each other, converting their mass into energy in the form of photons. This process is a direct consequence of Einstein's equation, E equals mc squared, where energy, E, is equal to mass, m, times the speed of light, c squared. The most striking difference between matter and antimatter is their charge. Electrons are negatively charged, while positrons are positively charged. Similarly, protons and antiprotons have opposite charges. This charge difference leads to a profound consequence. When a particle of matter meets its corresponding antiparticle, they annihilate each other in a burst of energy. This annihilation process is a direct demonstration of Einstein's famous equation, E equals mc squared, where energy, E, is equal to mass, m, times the speed of light, c squared. Despite these differences, both matter and antimatter interact with fundamental forces in the same way, adhering to the same laws of physics. One of the most profound questions in physics is why the universe is predominantly made of matter. The Big Bang should have created equal amounts of matter and antimatter, yet we observe a significant asymmetry. This discrepancy is known as the baryon asymmetry problem. Theories such as CP violation, charge parity violation, suggest that the laws of physics might be different for matter and antimatter, leading to a preference for matter in the early universe. Antimatter research has practical applications, such as medical imaging. Positron emission tomography, PET, scans use positrons to create detailed images of the body. Additionally, there is ongoing research into potential future technologies like antimatter propulsion for spacecraft. The asymmetry between matter and antimatter in the universe is a topic of intense research. The Big Bang should have produced equal amounts of matter and antimatter, yet our observable universe is predominantly made of matter. This discrepancy is known as the baryon asymmetry problem. Theories such as CP violation, charge parity violation, suggest that the laws of physics might be slightly different for matter and antimatter, leading to a preference for matter in the early universe. Ongoing research in this area aims to uncover the mechanisms behind this asymmetry. Facilities like the Large Hadron Collider, LHC, are crucial for studying antimatter. By colliding particles at high energies, scientists can create and observe antiparticles, providing insights into the fundamental nature of the universe. Scientists use magnetic traps to store and observe antimatter particles. These traps, known as pinning traps, use magnetic and electric fields to suspend antiparticles, allowing for detailed study without immediate annihilation. Particle accelerators like the LHC are essential tools for studying antimatter. By accelerating particles to high energies and colliding them, scientists can create and observe antiparticles. These experiments provide valuable insights into the nature of antimatter and its interactions. Additionally, antimatter traps, such as pinning traps, use magnetic and electric fields to suspend antiparticles, allowing for detailed study without immediate annihilation. These studies are crucial for understanding the fundamental properties of antimatter and its role in the universe. In our exploration, we've uncovered the profound differences between matter and antimatter. We've seen how these two entities, though opposite in charge and certain properties, are governed by the same fundamental forces. The annihilation process, a spectacular conversion of matter into energy, highlights the dynamic and interconnected nature of the universe. Understanding antimatter is not just a theoretical pursuit. It has practical applications in medicine, technology, and potentially in space exploration. As we continue to push the boundaries of science, antimatter remains a captivating frontier that could unlock new mysteries of the cosmos. Whether you're a student, a scientist, or simply curious about the universe, the study of antimatter offers endless possibilities and profound insights. Stay tuned for more journeys into the wonders of physics and the universe. Thank you for joining us on this exploration of antimatter versus matter. We hope you've gained a deeper appreciation for the intricate dance between these cosmic counterparts. Whether you're a student, a scientist, or simply curious about the universe, the study of antimatter offers endless possibilities and profound insights. As we continue to push the boundaries of science, antimatter remains a captivating frontier that could unlock new mysteries of the cosmos. Stay tuned for more journeys into the wonders of physics and the universe. Thank you for watching. If you're hungry for more knowledge, hit that like button and don't forget to subscribe. Your support is incredibly valuable to us.